record on this computer. So as a result, a dipole can also produce an electric field, and somehow the electric field produced is proportional to the dipole moment. And so therefore the dipole moment is like a coupling constant again. So basically it means that the stronger the dipole moment is, bigger the electric field produced. Right? But there are a few things that I should note in here. So dipole moment is a vector, right? So the dipole moment is a vector. So therefore, the electric field produced by the dipole moment at different points depends on that vector somehow. So there are these different situations in here. So I have just shown the situation where the point in question is on the symmetry axis of the dipole, in which case the electric field appears to be parallel to the dipole. But we know that if I take, for example, this point in here, where the position of the point relative to the dipole is perpendicular, I mean, that thing is 90 degrees, perpendicular to the dipole. In that case, it appears that the electric field is opposite. Okay. And I know that, for example, in some other situations, like, for example, if the point in question is somewhere in here, in that case, the electric field is making some kind of an angle. So I think it was like making an angle like that, for example. All right. It's not a, let me try to show it like that, right? So that, I mean, there's some kind of a complicated expression for the direction. Only when the point in question is on the axis, on the symmetry axis of the dipole, and when it is on the plane which is perpendicular to the dipole, let's say, only in those cases we can write down some clear expressions. Otherwise, the electric fields in such general points are more complicated, actually. It's actually quite complicated for this course. And so as a result, we are not going to do anything with this. And there's another feature in here. So the strength of the electric field is also dependent on that position as well. So here it is like 1/2 pi epsilon 0 r cube, 1/r cube. Here it appears that the electric field is, if I remember correctly, it is minus 1/4 pi epsilon 0 p divided by r cube. Okay, so this coefficient in front also changes. However, in all of these cases, the electric field is proportional to 1/r cube. All right, let's say it like this. So let's say it like that. So E field due to a charge, I mean, an ion, for example, that has a net charge. In that case, the electric field is proportional to 1/r squared. So let me say E charge in here. And the electric field due to a dipole, the electric field due to a dipole, this is proportional to 1/r cube. So the important point in here is that when R is large, this actually decays faster than this one. So let me say it like this: decays to 0 faster than the electric field due to a charge, which means something like this. If I plot, for example, the electric field produced by a charge, for example, it basically decays to 0. So let's say that this is the electric field due to a charge. And let me use a yellow color for the other one. So the electric field due to a dipole might be actually strong compared to the electric field due to a charge at close distances, but at large distances, it's always weaker, right? Let me show it like that. So that's just an exaggeration. So let's say this is electric field due to a dipole. So at long distances, we're talking about the distances much larger than the size of the molecule usually. at long distances, the electric field due to a charge is always stronger. Electric field due to a dipole is weaker because of this 1 over r cube behavior, right? So this is 1 over r cube, let me say 1 over r cube in here. And the electric field due to a charge is a little bit more stronger. It is 1 over r squared. So what if the molecule doesn't have any dipole moments? It has a quadrupole moment, for example, like the carbon dioxide molecule. In that case, the electric field goes like 1 over r to the 4, right? It's even much more weaker than the dipole. And so as a result, this is why we usually forget about these nonpolar molecules. If they don't have any dipole moment, then they don't have any effect at all. At long distances, they don't have any effect. Okay. I think I'm going to say one more thing in here, and then before passing to the other one. I think in chemistry, you have heard about these van der Waals forces. I'm not going to say anything in here, but these are essentially forces between neutral molecules, or a neutral molecule and an ion at best. So they actually arise from this dipolar property. So you can actually think of it as the forces due to the fields produced by the dipoles. Let me say it like this: forces due to fields created by dipoles. You can think of them like that, but there are some certain aspects in here. So even though, for example, helium atom, it doesn't have any dipole moment. It doesn't even have any quadrupole moment, but there's some kind of a charge distribution. So as a result, a helium atom, when it is placed next to a helium atom, they somehow start interacting with each other, because somehow they become affected by their presence, and some sort of oscillating dipole moment is produced because of this interaction, right? So as a result, even though we have like two helium atoms, which might be too far away, there will still be an effective, some kind of a force between them, which kind of arises because of these kind of dipoles that are somehow produced instantaneously because of their presence. So all of these kind of forces are called van der Waals forces. Usually they are attractive, and so as a result, they form an important part of this cohesion forces that keep the matter together. So for example, helium liquid is possible because of such kind of forces, right? Helium in the liquid form is possible, or in solid form is possible because of these forces. In any case, this is something else, because I mean, when people mention about these van der Waals forces, people usually think of them as some kind of mystical things. Well, everything comes from the Coulomb source, basically, right? So let's just keep this in mind. Now, this is the second aspect, right? So a molecule with a dipole moment is placed inside an externally produced I say just external, right? Electric field. Okay, so we have this kind of a situation in here. So I'm going to show the dipole moment like that, P, and then we have some kind of an electric field in space. So it's basically everywhere. So I'm going to do it like that. So this electric field is externally produced. So I don't know, some other charges elsewhere produce these. So probably there are some negative charges in here or some positive charges in here that produce this electric field. So this external electric field might be uniform or non-uniform. So depending on the situation, we have different conclusions. In any case, I'm going to assume that this electric field is uniform, because in the non-uniform case there are some complicating things. So assume E is uniform. So I'm going to do everything with these assumptions. So when I place an dipole inside an external electric field, it also becomes affected by that electric field. So therefore, the motion of the dipole should change. So we can quantify this by the net force applied on it and the net torque applied on it. And we are just going to compute both of these quantities. Right? Again, let's remember these two aspects of the interaction. This dipole produces an electric field. So there's actually an additional electric field in here. Sorry about that. There's an additional electric field in here produced by this dipole. We're not talking about this thing in here. So this electric field exists, but what I shown by E in here is not that electric field. So I'm forgetting about the field produced by the dipole. Just forget about it. This field is produced by some other charges or some other dipoles perhaps. And we would like to see how these external charges apply a force on this one. Okay. So again, I'm going to assume that this is uniform. So I'll start with the net force. So what I do is this basically. First of all, I consider the dipole as, again, in the simplest form, a minus charge and a plus charge separated in space. And then I just derive the expression of the net force by just looking at this picture. So net force on the dipole. I think I'm going to use this picture. So that means I have a negative charge in here, positive charge in here. So that's minus Q, that's plus Q. There's an electric field in here along that direction. Yeah, I think I'm going to just show a single vector in here, but the electric field is everywhere. Just keep this in mind. Let me use a green color. First of all, let me show this. We know that the force applied on a charge is equal to charge multiplied with the electric field. So as a result, we can use this formula in here. So we can then first consider the force applied on the positive charge. So this is F plus. This is parallel to the electric field because the charge is positive. And then there's this force applied by the negative charge. And this is F minus. And this time this is opposite to the electric field. So F minus is minus Q times E. And since we have assumed that the electric field is uniform, in that case, these two forces are equal and opposite. And so therefore the net force is equal to 0. Okay, so that's basically the conclusion in here. There is no force applied on a dipole in a uniform electric field. So the net force on a dipole is always equal to 0 in a uniform electric field. So this might be a little bit confusing for some people because I'm stressing on this uniformity in here. If the electric field is not uniform, so that means like the electric field that, this positive charge experiences is different than the electric field that this negative charge experiences, for example. In that case, there is a net force on the dipole. Right? The net force is non-zero. But this is a complicated case that I don't want to treat in here. So as a result, we just look at the situation in here that when the electric field is uniform. So that's the important point. There's no net force. So as a result, this dipole cannot change its location, cannot accelerate, right? But you can see that, so this distance is usually fixed. This is a molecule, so these two charges are bound to each other by some kind of forces. So as a result, that distance doesn't change in any case. So as a result, you can see that because of these forces, which are equal and opposite, these forces can rotate the dipole. So that means it applies a torque. Okay, and then therefore we compute the net torque applied on a dipole. Right. So I'm going to compute this in a few different places, in a few different ways. Let's start with this simple idea. So there's a negative charge in here. There's a force applied on it along that direct. Yeah, let me first draw this. Right, I'm going to draw a line in here. So that distance is d. And let's see, there's an electric field in here along this direction. And let's say that this angle is theta. So I'm going to show with green colors these forces. So this force is like that, and that force is like this. So both forces have the magnitude Q times E, but they have different directions. Again, just keep in mind that this QE is the component of a vector along this direction, and this QE is the component of a vector along this direction. So, so these are components along the shown directions. So this implies that these vectors are in opposite directions, and they have equal magnitudes. All right, so how can I compute the torque? Let's say net torque in here. In that case, there are a few different methods. I have talked about this thing before. So first you have to choose the origin. So you can do that in many different ways, but let's suppose that I choose my origin at the negative charge, origin. So in that case, net torque is equal to the net torque applied on the negative charge plus the net torque applied on the positive charge. But since the negative charge is at the origin, the torque applied on it is equal to 0. And on the positive charge, the torque applied is basically, I need to multiply the perpendicular components of the force with that distance in here. So it's something like this. I don't know. I mean, there are different ways of computing this, if you remember. It's like the perpendicular component of the distance times the force. Or I can write this thing down as the distance multiplied with the perpendicular component of the force. Or I can write it as d times f times sine of the angle between them, right? I can use any of these approaches, but let me start with the first one. In that case, we have a situation like that. This is d, this is the origin in here, and the force is this. This is the force, this is Q times E. What we do is we just extend this force. This is the line of force, if you remember. And then we compute the distance of that origin to that line of force. It is that distance, which is basically d perp, and that's d sine theta, because that angle is theta. And so as a result, the net torque is therefore d times q times e times sine theta. Right, this is one approach. The other approach is like, let me show it in here. So this is the force basically, but I take the perpendicular component of that force to that position in here and forget about this parallel component. And the perpendicular component is QE times sine theta. So as a result, in all of these cases, you get the same kind of an expression. All right. What's the direction? I can show the torque in many different ways, but I mean, I can show it like that by showing the direction that this would rotate, or I can use a right-hand rule, in which case the four fingers show the direction of the rotation, and the thumb therefore shows the direction of the torque. That's basically into the screen in that case. Okay. So in any case, or I can do it like this. I have negative charge and positive charge in here, right? It is this point. So I can choose my origin at the midpoint, for example. The origin can be chosen like that. So this is the force applied on the positive charge. This is the force applied on the negative charge. That distance is d over 2. That distance is also d over 2. And I still have this theta thing, the angle in here. So in that case, the net torque is, well, there will be a torque applied on both positive and negative charges. And you need to use the same algebra for computing both. So for the torque applied on the negative charge, this is the distance to the origin. That's the magnitude of the force, and that's the sine theta. You can see that this direction is like that. And here for the positive charge, it's the same. You can see that the torque applied on the positive charge is also in the same direction. So therefore, the amount of the torque is the same. Okay, so we can continue like that. It doesn't matter. But if you remember in the last semester, I have said something like this. So let's say it like this. If the net force is equal to 0, then the net torque does not depend on where we choose the origin. In the last semester, I have talked about this thing for situations where, I mean, there might be some situations where by choosing the origin in an appropriate way, you could make the net external torque to be equal to 0 in some problems. But there are some problems where if the net force is equal to 0, then it's not going to help you. So if there is a net torque, then there's always a net torque wherever you choose the origin. But in any case, you can actually apply this thing in here. So the choice of the origin is irrelevant because the net force is equal to 0. You always get the same net torque wherever you choose the origin. Okay, so it doesn't matter where you choose. You can choose it outside as well. You can choose the origin somewhere in here as well. No problem at all. You always get the same thing. In any case, what's important is the magnitude, the expression in here. So that's d times q times e times sine theta. And you can see that there's always a product of the distance between the charges and the charges. So that's basically the dipole moment magnitude. So the net torque is PE times sine theta. So let me show this picture like that. So let's say it like this. This is the dipole moment vector. This is the electric field vector. Theta is the angle between them. In this kind of a situation, the the torque has a magnitude which is given as the product of these two vector quantities magnitudes multiplied with sine theta. There should also be a direction, but let's talk about the direction later. But the important point in here is that the net torque in here depends only on these quantities. So we have been talking about the interaction between the field and the dipole. We quantify the field with the electric field vector, that's E. We quantify the dipole by its dipole moment. And there are no other expressions in here except the geometrical angle between these two vectors. Okay, so as a result, it is the simplest possible expression, basically. We don't have any distances or anything like that. We can even simplify further. We just noticed that this torque is also a vector. It's just expressed as the product of two vectors. So if you multiply two vectors, you can multiply two vectors in two different ways. In one way, the result is a scalar, and the other way, the result is a vector. Here, probably I should use the last one. So as a result, the vector product of two vectors should produce a vector. So therefore, probably I should have something like this. The net torque should be equal to the vector product of these two vectors, the cross product. Right, so if you remember this, then you can easily write down the magnitude, no problem with this. So as a result, this is a little bit more fundamental formula than this one. But let me derive this then. So that's the derivation of the vector product. So I'm just going to, yeah, forget about this. Let's just say that there are many charges in here. And I choose my origin somewhere in here. And let's say that the position of this one is R1 and so on. And then there's an electric field, of course, in here. And so as a result, on each of these charges, there's this force applied, which is basically the charge multiplied with the electric field. Okay. So let's say it like this. So Fi is the Qi times E. So that's the force on the charge Qi. I don't want to write anything in here. So the net torque in that case, if you remember what the net torque on applied by a certain force is, so it's basically the position of where the force is applied cross product with the force. It is this summation expression. But in here, if I write down the force expression, force is always charge multiplied with the electric field. You can see that I then have an expression like charge multiplied with the positions of these things. This is, well, we take the cross product of this thing with the electric field. But then I have defined this as the dipole moment of this, whatever, the charge configuration. And so therefore the net torque is equal to the cross product of the dipole moment with the electric field. Right, this is the more formal and actually the perfect derivation. So we actually derived it for all possible dipole configurations. Right, I don't know if you have any questions in here, but let's just go to the physics part. The physics part is that if you place a dipole moment inside an external electric field, it doesn't move, it doesn't accelerate, its center of mass doesn't move, but it rotates. Because there is no net force on the dipole, there is a net torque. Okay. So I don't know if you have any questions in here, but let me just look at a few situations in here. So I'm going to consider, sorry about that. I'm going to consider an electric field. In all of these cases, the electric field is pointing towards right? And I'm going to look at several situations. So if the dipole is like that, right? We need to use the right-hand rule at this point all the time. So I suggest that you do this because I'm going to show you some directions in here. So we know how to take the cross product. So it is P cross E, right? And so therefore, P cross E, in that case, the thumb should be pointing along the direction of the first vector P. The index finger is pointing along the direction of the electric field. and the middle finger shows the direction of the torque in that case. The torque, which is basically in this situation, therefore, is pointing into the screen. So let me use a different color for this one. So in that case, the torque is pointing. This is the net torque. Torque is pointing into the screen, which means this torque basically causes an angular acceleration, again by using the right-hand rule along that direction. So this is the direction in which this dipole will accelerate. Okay, so this is the situation in here. So what happens if we have this? I don't know. It doesn't matter if the dipole is oriented like that, right? In that case too, you can easily see that the net torque is still pointing into the screen. So again, this would be rotated like that. But if the dipole is oriented like this, this is the dipole moment. In this case, the net torque is pointing out of the screen. Sorry, this has to be white. So the net torque is this time pointing out of the screen, which means this is going to rotate like that. Right, let me put the arrow sign in here, right? So this basically tells you that in general, the electric dipole moment tends to orient parallel to the electric field, right? So this is basically the stable orientation, because in that case, for example, in that orientation, net torque is equal to 0. And also, if the dipole is oriented slightly off along this direction or along this direction, there is always a restoring torque that tries to restore the dipole moment back into the parallel orientation. So that's a restoring torque. So we say that this is the stable equilibrium position. Okay. Equilibrium position because the net torque is equal to 0. So if you place a dipole in that orientation, it will stay there forever. It is stable because if this dipole moment is slightly oriented off from the orientation, then there will be a restoring torque that will bring the orientation back into the parallel position. So therefore, this is stable, right? So basically, this is the situation where the net torque is, I mean, since the vectors are parallel to each other, the cross product of parallel vectors is always equal to 0. So the net torque is equal to 0 in here, but it's not only that, there's also a stability in here. On the other hand, there's this other orientation in here. So let me also draw this, in which case the dipole moment of the molecule is pointing opposite. This is also an equilibrium because the net torque is again 0. So basically the cross product of two parallel vectors or anti-parallel vectors, these are always equal to 0. This is also an equilibrium position, but it is unstable. Right. So as a result, I mean, if you place the dipole inside that location with exact orientation, it will ideally stay there forever, but it won't because there will always be small deviations from this ideal orientation. So as a result, once you have this deviation, the torque somehow removes the dipole from that orientation and then makes it parallel. Okay, so I think this is one of the important things. So from the perspective of energy, potential energy, if you remember that discussion in the previous semester, stable equilibrium positions are the positions where the potential energy is a minimum. And unstable equilibrium positions are the places where the potential energy is still an extremum, but this time this is a maximum. Okay, so we haven't said anything about the potential energy yet. We are going to say it. But from the energy perspective, you can understand these equilibrium and the equilibrium positions like that. One is a minimum equilibrium, one is a minimum potential energy orientation. The other one is maximum. Okay, so in any case, let's just go back to this water video. Just remember this, right? In that case, this was one of the effects. If you apply an electric field to the water molecules, they rotate and somehow they try to orient parallel to the electric field. So that's the first effect in there. And there are some aspects in there. So normally these molecules should have this rotational kinetic energy as well. So, I mean, the total energy should be conserved. So therefore, this should be swinging like a pendulum, for example. Let me make this pendulum analogy, right? Sorry about this thing, but there are actually quite similarities in here, analogy. So in the case of pendulum, so I'm going to assume that this pendulum is like, this is not a string, but this is a rod. Let's say that this is a rod, this is mass, so that's fixed in here, whatever. There's this swinging motion in here. So in that case, the gravity plays the role of the electric field, and somehow that distance, sorry about this, that vector in here plays the role of the dipole moment, right? You can actually understand it like that. So as a result, we have these situations in here where if this vector, the pendulum is oriented perfectly parallel to the gravity, we have the stable equilibrium position, and on the other hand, if the pendulum is what they call inverted, so that means it is this situation in here where the bob is like above. So since this is a rod, it can stay upright like that. So that's an equilibrium position, but it's an unstable equilibrium position. So that's an unstable equilibrium position. So as a result, if you just leave a pendulum like that, it will just swing back. In any case, so for any given orientation of the pendulum, we have the swinging motion of the pendulum. So there's actually a complete parallel between the motion of the pendulum and the motion of a dipole. So if you have a dipole in here, a molecule, a water molecule, for example, and you apply an electric field, it will swing like a pendulum. But eventually, of course, this is going to stop because of the energy is lost somewhere to other molecules because of collisions and things like that. And just like the pendulum is tend to become oriented perfectly in the downward position, after some times you are going to find most of these molecular dipoles to be oriented parallel to the electric field, right? So when you apply an electric field, first they start swinging, but eventually they are going to stop, and then we will see that all of the molecules, I mean, most of the molecules have this dipole moments oriented almost parallel to the electric field. There will still be some kind of swinging because of this molecular randomness, but there will be some kind of a net average dipole moment which is oriented parallel to the electric field. So this is a little bit complicated process, but this is the part that you don't need to understand. But when they say, like, when you apply an electric field to water, the molecules orient themselves in such a way that they, whatever this dipole moment becomes parallel to the electric field. This is essentially true, right? But there are some important physical processes that's happening in there. So there's some kind of dissipation, basically, that makes this thing possible. Okay, so that's the first one. Unfortunately, I won't be able to explain this whole thing, water experiment in here, but let's then pass to the potential energy thing. Energy of dipole inside an external electric field. Okay, so I think I can do a derivation in here. So there are some parts that people usually get confused about this, but I'm just going to do it like this. So first, let me clarify some of the issues. There's an electric field in here. This is the dipole, and the dipole moment is like that. So that's the dipole moment. And I know that there's a torque in here. This time I'm going to show the torque like that. So let me not write the net torque in here. But let me say that this is the torque applied by the electric field. Right? Electric field. So as a result, I'm going to write the subscript electric in here. So think about any kind of an orientation change. We can talk about the work done by the electric field on the dipole. So it's the work done by the, again, external electric field on the dipole. Okay, so normally work done is, this is the electric work done. Work done is basically force dotted with displacement, but we don't have a net force in here. We have a torque. So as a result, I can replace this expression with the torque, which is the electric torque in here, dotted with the displacement, and in that case, the displacement is the angle. And well, I need to integrate this because we cannot have this uniform torque in here. So because the torque depends on the angle. Okay, so this is the work done by the electric field on the dipole. But we know that the electric work done, the electric force, sorry, is conservative. So this is a conservative force. The electric force is actually conservative, but in any case, we can also show that this is the case in here. So therefore, I can express this work done by the electric field in terms of a potential energy. So as a result, we then equate this to the negative of the change in the electric potential energy of the dipole. Okay, so this is the first part. This is the definition part. I know that some of you will get confused about this minus sign and things like that. So as a result, if you don't remember this concepts like the work done and its relationship to the potential energy change, conservative forces and things like that, I suggest that you read that part of the textbook again, right? So this part is kind of important because I'm going to use these kind of concepts. The second thing is that in some cases, I would like to apply another force on the dipole. So I mean, I don't leave it alone with this torque applied by the electric field. So as a result, I apply a torque, an additional torque on the dipole by myself. So I'm going to use this red color to show the torque that I'm going to apply. So let's say that I somehow use my hand to actually move this dipole, right? So I'm going to do it like this. Use my hand to rotate the dipole from an angle an initial angle to a final angle, such that the dipole is always at rest. I think this is nonsense, but let's say that the angular velocity is almost equal to 0. So that means kinetic energy is equal to 0. So that's the one that I'm concerned with. So there should be no change in the kinetic energy. All right, so in that case, what I need to do is to apply a torque by my hand, which is almost equal to the magnitude of the electric torque, but opposite in direction. Okay. So I don't have much time. So as a result, let me just do it like this. So this is the work kinetic energy theorem. So basically the net work done is equal to the change in the kinetic energy. But there are these two forces in here, work done by the hand. So there's also electric work done. And the change in the kinetic energy, we just assume this to be equal to 0. So that's because of my assumption in here. So this is the part that I want to compute. So that's the negative of the change in the electric potential energy. So as a result, this then implies that the work done by the hand is equal to the change in the potential energy of the electric due to the electric force. So that's the one that I want to compute, but I'm going to use this picture in that case, right? So why am I using this kind of a picture? I just want to explain things like that, right? Because people usually get confused about these kind of things all the time. So this angle is theta. I know that the torque applied by, this is red, torque applied by the hand is along that direction, and d theta is in the same direction, right? So torque applied by the hand as a vector and d theta are in the same direction. So that means their dot product dotted with d theta, that's equal to basically the magnitude of the torque multiplied with the magnitude of the angular change multiplied with the cosine of the angle between them, and that's equal to +1, right? So as a result, work done by the hand is, normally it is this, let's see, it is the dot product of the torque with the displacement. I mean, force dotted with the displacement. I replace this with the product of the torque's magnitude and the change in the angle. Well, the magnitude of the torque applied by the hand is equal to the magnitude of the torque applied by the electric field. In magnitude, they are equal. So as a result, I need to integrate this. The integral of sine theta is cosine theta. Sorry, it's minus cosine theta, sorry. So as a result, this is equal to minus PE cosine theta F. And then it is minus PE cosine theta I. And that's equal to the change in the electric potential energy, because this is something that I have deduced in here, right? So because of that, then we just choose the electric potential energy as minus PE times cosine theta. All right, that's the formal derivation of that expression. But in any case, this is again a complicated expression. We usually express it in terms of the dot product. Dot product of the electric dipole moment with the electric field gives us the potential energy of the dipole that describes its interaction with the external electric field. I just take the dot product of the electric field with the dipole moment. I think I'm going to stop, but I should say something more. Yeah, I think I'm going to say it like this. So this is the expression in here, but there are these two situations in here that are of importance. When the dipole moment and the electric field are parallel to each other, in that case, the electric dipole moment is equal to minus P times E in magnitude. So that's the minimum possible value. So this expression is always between minus PE and plus PE, and minus PE is the minimum possible situation. So therefore, this is the orientation where the electric dipole moment is in the stable equilibrium position. And so therefore, this corresponds to the situation where the potential energy is minimum. So that's the stable equilibrium. And then we have the this other case. The electric field is like that. The dipole moment is opposite. In that case, the potential energy is positive PE, which is the maximum possible value of that potential energy. So therefore, this corresponds to the unstable equilibrium situation. All right, let me also spend some time on comparing these two. The torque was equal to P cross E, and the potential energy is equal to minus P dot E. So in both of these expressions, we have the product of two vectors, but in one case, the result is a vector, and the other case, the result is a scalar. So therefore, these two products are different. One is the dot product that produces scalar. Energy is a scalar, so therefore, I have to use the dot product for the potential energy. There's an extra minus sign in here, but by using the idea that the parallel orientation is the stable equilibrium situation, you can easily decide whether the sign is positive or negative. So that's, I'm just going to leave this out. In any case, the torque is a vector, so therefore this is given as a vector product. Just notice that this is basically, I mean, the order is important in here in the cross product, if you remember. So just try to remember this order. So because of that, the order is extremely important. Do not make any mistakes like that. So that's important. The second thing is this, I don't know if we have done this discussion before or not. So the unit of the torque is Newton meters. I mean, we're multiplying a force with a quantity with a dimension of length. And the unit of the energy is also Newton meters. And we have said that, well, the torque has the same unit as the energy, but since it's a different concept, it's not an energy concept. It's a different concept. So as a result, in that case, we just refrain from using the joules for expressing the torque. So we just use the Newton meters, right? So in any case, so we have a situation like the dipole moment and the electric field, their products have the dimensions of energy. But in one case, a particular product gives you a torque, and the unit has to be expressed as like Newton meters. And the other case, it gives you an energy, in which case the unit used should be the joules, right? So as a result, there are actually quite similarities between these two, but I mean, we have different concepts. So as a result, in that case, we use different mathematical operations to express the torque and the potential energy. Okay, so I think this is kind of important because even if you didn't know how to derive these physically, by just looking at the nature of these relationships, you could have guessed them, right? Because you know that the torque is a vector, so therefore it should be some kind of a vector expression should be obtained from this operation. Okay, so I think this is quite significant. And so as a result, that's why I'm stressing on this thing. So let me stop here. I'm a little bit late on offline videos, but I'm going to provide some offline videos, both from the electric field due to continuous charge distributions and from the dipoles. And so just wait for it. And there will also be an online homework too. Okay, so let me stop.